Hello there. In this video we're going to talk about a very important theorem known as the Central Limit Theorem and some of its consequences and how they can be used in our statistical analysis process. Let us first assume a couple assumptions. Let us first assume that we have a population P and that population has a particular size, say capital M. This is not really going to be important to us because we're just going to take a bunch of samples from it anyway and then put them back. So it's possible that two different samples can serve the same exact person. But let us assume that that population has a mean mu and a variance sigma squared, hence a standard deviation sigma. And let us assume that this population also has some distribution on its values, and let us call that population distribution phi. Now it doesn't matter what phi looks like. It could be uniform, it could be normal, symmetric, skewed left, skewed right, binomial, Poisson. It doesn't matter. And you'll eventually see why it doesn't matter, but we need to take note of it at this point. Now, of course, usually you do not know what mu and sigma squared are ahead of time. That's why you're going to take samples from it. So let us consider taking a series of samples, and let us call them samples S, and let's assume that the size of the samples is little m. And again, I say, let us assume they're sampled with replacement. So two different people can have the same exact values, hence they are independent samples. So from here, what can we say? Alright, so let us quickly take a note of something. So let us assume person 1 has a sample. That sample has values x1, x2, all the way out to xm. And since you have a sample in your hand, then that means you can find the sample mean of that sample. No big deal. And let us assume that another person does the same exact thing. They go out and get a sample, x1, x2, all the way out to xn. And that sample is also going to have a sample mean. And it's important to note that this x1 not be equal to that x1. It's possible that that x1 could be that x2, possibly. So these indices for these x values are unique with respect to the sample for which it comes from. And of course, you can continue this process as many times as you want. So in general, you could have a kth sample where k could be 100. Again, it's going to have x1, x2, out to some xn. And that sample is going to have its mean. And we're going to continue this on until we're satisfied, whatever that means. So if this is true, what do we have? So therefore, x1 is a random variable in its own right. So x1 represents the random variable that could take any of these values from each of these samples. x2 also, x3 also, xk also, and so forth. So all of these values are random variables. If that is true, this last one should be xn. So that means that x bar, which is defined to be equal to the sum or the average from k is equal to 1 to n of these random variables xk, also is a random variable, which we had discussed in a couple previous videos. So let us quickly summarize a couple things that we know. So x1, x2, all the way out to xn are all independent random variables. So that's the first thing that we know. Also, x1, x2, all the way down to xn are all identically distributed. And why is that? Well, that's since they all come from the same population. So if that is true, that means x1, x2, all the way down to xn are all identically distributed and independent random variables. So what else can we say? So from the previous videos, we already know two important conclusions. The first one being that the expected value of x bar, well, before we get to that, firstly, the expected value of x is equal to mu, and that's going to be true for all values x. And the variance for all those values is going to be equal to sigma squared. And also we have proven in the past that the expected value of the sample mean random variable equals mu. And the variance of the sample mean random variable is going to be equal to sigma squared divided by n. So these are both true. Now, there is one other property that the central limit theorem has that we have yet to discuss. So if you repeat the sampling process enough times, so first you have, say, 1 sample mean, 2 sample mean, 100 sample means, and so on, x bar still is discrete, but may be treated as a continuous random variable. Right, so let's assume if you have just 2 sample means, you can have a sample mean there, a sample mean over here. But if you have a bunch of more sample means, you could have, say, a more sample means there. But if you continue this process, then you're going to have, a more closer set of values. And eventually, these values are going to be so close together that they're distribution, right? So we pretty much can connect these dots. So the question then becomes, well, what is the shape that these values are going to take? Well, if that is the case, then the central limit theorem states this property. Then the values of the sampling distribution of the sample means converge to a normal distribution with mean mu. So that is, this distribution that it's going to get close to is going to get close to this, what we call a normal distribution, whatever that is. But the pretty much middle of this distribution is going to be mu. So what is this distribution that it's getting close to? So of course this is going to be our x bar axis, and this is going to be, let's call it the frequency distribution for x bar. And it's going to get close to this shape. So this shape is what we call a normal distribution. Normal. And nonetheless, it is a symmetric distribution, but that is not the only thing that pretty much characterizes it to be symmetric. And of course, this is going to be mu. But this shape does have a function value that it's going to approach, but I'm not going to prove it here. But this function is actually going to come out to 1 divided by sigma times the square root of 2 pi times e to the 1/2, negative 1/2, times x minus mu divided by sigma, the quantity squared. Now, that formula may be a little daunting or complicated to look at, but, that's one of the consequences of the central limit theorem. And I omit the proof here. But that's interesting. So it doesn't matter pretty much what's going on here. And that's going to be the last important thing. And this is going to be regardless of the population distribution. Phi x. So it doesn't matter if the original population is uniform, skewed left, skewed right, bimodal, or pretty much any type of shape that you want. If you take a bunch of sample means, if you do it enough times, the random variable x bar is going to be continuous, and it's going to start converging to this function, which we call the normal distribution. And that's very, very important. So let us summarize these concepts and sort of give a last discussion of its consequences. So let x1, x2, and all the way out to xn be independent and identically distributed random variables. From a population P that has mean mu and standard deviation sigma, and x bar being the random variable defined by the sum of all our x values xk, where k is ranging from 1 to m. Then, the first conclusion of the central limit theorem says this. So, conclusion 1, the expected value of the sampling distribution of sampling means is going to be equal to mu. The standard deviation of the sampling distribution of sample means is going to be equal to sigma over the square root of m. And remember, we have other alternative ways of writing this. Some people can call this mu x bar, and some people call this x bar, when some people even refer to this as the standard error of the estimate, x bar. And most of all, the distribution of x bar converges to the normal distribution, regardless of population distribution. And this is always going to hold true. This will hold true as long as the sample size n is sufficiently large. Some books, or maybe you even learned this back in the day, some people use this rule that n must be bigger than or equal to 30. This rule is not one that should be trusted always. And I even recommend just, forgetting it. Because if you have a population that is extremely skewed left or bimodal on the left and right tails of the distribution, then it's possible that you may need even a larger sample size, maybe 50, maybe 100, maybe 1,000. It also depends on the population size as well. So pretty much use as a rule of thumb sufficiently large. If the population is already symmetric and, normal itself, sometimes a smaller sample size, maybe 20 or even 15, would be sufficient, as long as you repeat this sequence of sampling processes a lot of times. But that's pretty much a summary of the central limit theorem and its consequences. And it really does have a lot of important results. Namely, it gives a connection between the population parameters mu and sigma, even though we do not necessarily know what they are. But if we do the sampling process enough times, the central limit theorem then comes into play, and then we can use these consequences to sort of help us figure out what mu and sigma are.